All right, Thompson's model we talked about a while back before fall break. We talked about Thompson's model, Rutherford's model. Actually, let me scoot that down just a hair there. And the homework tonight, just to put this up here, the 2s and the 3s. So Thompson's model of the atom had the electrons stationary. Then Rutherford came along and said his was like electrons were going around the atom like bees around a hive. And we know that they can't be stationary or that they can't be random. So we're going to start talking about Bohr's model of the atom, and this was actually, Bohr was a student of Rutherford, and he improved upon Rutherford's model. Now, one of you might be amazing one day as well by being a student of mine, so keep that in mind. All right, so Bohr's hydrogen atom, and again, we're talking about a simple atom where we have one proton, one electron. Bohr was able to combine the ideas of classical physics and new quantum theory to explain the structure of the hydrogen atom. Now, that's all exciting and everything, but here's what Bohr came up with in a nutshell. Were these blanks here? The absorb and excited?
Yeah. Okay.
Excited. And what we're going to talk about, and I'm going to explain it with this picture of the ladder that looks kind of interesting, so to speak. When we talk about orbitals, or where electrons are at, it's kind of like a planetary system, where Mercury, Venus, and Earth are relatively close to the Sun, and then we start getting farther away, and then the other planets get farther and farther. So if we look up here and we say, okay, well, our nucleus, the nucleus, there's a better idea. If the nucleus is located right there on top, then we're going to say that the electrons that are closest to that nucleus are going to be more strongly attracted. And then as we go farther and farther away, so as we get farther away from the ladder, these electrons that are farthest away from the nucleus are going to be easiest to pick off or remove. And in that case, when an atom absorbs energy, okay, when an atom absorbs energy, it gets excited. And when atoms get excited, electrons either leave or they're shared with somebody else, but typically they'll get excited and leave or go to a higher energy level. And then we'll talk about how that electron, once it stops receiving that energy, returns back and changes that energy into something pretty cool. So when we look at energy levels for electrons, think of it like this strange ladder. That is a strange ladder. And the key here is that the energy levels where electrons are located are not equal. So when we say we're going from the first to the second energy level, there's a difference in the energy needed to go from those levels. And then we go from the first to like the 8th or 9th, okay, there's another set of energy that's associated with that. And here's what's happening. Okay, there's no blanks there. I'm going to explain the picture. When an atom receives some energy, okay, and in AP Chem, we'll talk more about this a lot more detail with PES, which is Photoelectron Spectroscopy, which we don't even touch in here. But this is what I'm about to explain to you in the Clip Notes version. When energy is absorbed into the atom, electrons, or certain electrons, will absorb that energy. They'll get excited, and they'll jump from maybe this energy level to another energy level. Once that energy has gone away, then that electron will return back to what's called its ground state. Now, ground state, what do you think ground state means in terms of vocab there? The lowest, or the most stable. So in other words, like right now, we're all chilling, we're all kind of digesting our breakfast, we're trying to figure out what the crap is he talking about here. But if somebody busted through the doors and started firing off machine guns, I bet some of you might get a little bit excited by that. So that would cause you to jump out of your chair or grab Gavin and use him as a body shield or something like that. Okay? But after Mr. Craig takes care of the gunman, then we're all going to settle down. Now, that's all right. But what happens is, as the energy is absorbed into the atom and that electron jumps to a higher energy level, when that energy dissipates, then that energy is changed into a photon of light. So like when you look over at the lava lamps over there, what we're doing is, or what it is doing, is exciting those electrons in there, and it's returning back to its ground state, emitting a certain color of light. So when it absorbs energy and then releases that energy, it changes into a photon of light. So depending on how much energy is being absorbed or released depends on the color of light. So let me examine all those. Okay. So if we have, say, something like here we're absorbing 656 nanometers of energy, then we might get something that's kind of a red light where versus a blue light. Now, the nice thing is, yeah.
Do different types of atoms make different light?
They do. Yeah, so like when you talk about neon lights versus like krypton and other things like that, they do emit different colors.
Can all atoms make light?
Technically, yes, depending on how you can excite those electrons. Yep. Now, excited atoms will emit energy as they return to their lower energy level, and that's what I want you to get out of this. So atoms absorb energy, the electrons get excited, and it's only the electrons, because the nucleus is locked in, it's not going anywhere. So the electrons move to a higher energy level, and then as that energy dissipates, they return and release that energy as a photon of light. So the statement here, when atoms absorb energy, their electrons move to a higher energy level. These electrons lose energy by emitting light when they return, and they can emit different colors. And I can't remember if I think there is either today or the next time we talk, there's what's called a blueprint. In other words, if you ever go into astronomy and you want to know what a star is made up of, we can't go to a star and check and see what it's made of, but we can look at its spectrum. We can see the light that it's emitting and say, oh, there's carbon there, there's nitrogen there, etc. So that's what we'll use. All right, the electromagnetic spectrum, let me go back to yesterday. This is the electromagnetic spectrum, which deals with all light, not just the visible light. Okay, and again, keeping in mind that the visible spectrum is a really small section, and I think the one on the wall actually is a little more accurate. This one isn't to scale as well. Did somebody just sneeze?
Yeah.
What? I don't know what that was. Okay, but so there is the electromagnetic spectrum, and I think I have another one here. The electromagnetic spectrum, waves are produced by a combination of electrical and magnetic fields. All the electromagnetic waves travel at the same speed, which is the speed of light. And we're going to use this value here, 3.0 times 10 to the 8 meters per second. But I think lately they've been coming out with this, but you know what? In my book, that's still 3.0 times 10 to the 8, so we're going to keep it simple. Okay. Whoa. Hit something. So, yeah, that number's nice, but we'll keep it simple to 3.0. Okay. The electromagnetic spectrum includes all of this light, and I think you have that graphic in your notes. And what this is showing is the frequency for the radio waves are low, because the wavelengths are long, and that the energy is low. What these arrows are representing is that going from here to here, so starting off here, it gets higher as we go down. That's what I want you to know. So if I were to ask you which has higher frequency, does infrared or ultraviolet have higher frequency? Ultraviolet. That's a test question, okay? Things like that, so be sure you can answer that. Or which one has higher wavelength, okay? Then you have to know that it's the inverse relationship. Okay. And then for whatever reason, I have another picture of another electromagnetic spectrum. And here's an image of how you can make a rainbow. Exciting. All right. This equation here is the other equation that we'll be using, and that'll be the second equation that we'll have on the quiz for Friday. So you have the E equation and then you have the C equation. Okay, the C equation deals with the speed of light. Okay, so this is our constant, and again, this is a constant. And the speed of light is 3.0 times 10 to the 8, and that's meters per second. Okay, that's pretty fast. I can't remember what it is in miles per hour. I think 181,000 miles per hour, but we don't care. Keeping that in perspective, if a photon left the sun and came to Earth, how long would it take? 8 minutes. Good. Okay. This, what does that represent? That's from yesterday. That looks like the dinosaur. Lambda, which represents what? Not the frequency. Not hertz, that's frequency. Wavelength, yeah, the weird long name. So wavelength.
The first thing I said was wavelength.
And the unit for wavelength is in meters. Okay, so that's wavelength. So there is wavelength. And then, what does the last one represent? Frequency, good. So frequency, let's use a different color. So frequency is that. And what's the unit for frequency? Hertz, which is better, is
something or 1 over
1 over seconds. Good. So think about it. If I multiply wavelength times frequency, what's my unit going to be? Meters over seconds. Yeah. Okay. So we have a constant, which is the speed of light, and we have our wavelength, which is in meters, our frequency, which is in 1 over seconds, or hertz. Okay. Now, we'll do some calculations with that here in a moment. All right, clean all that up. All right, so a couple things here. Frequency increases as the wavelength decreases. Why is that? Because they're inversely related. So it's an inverse relationship. As the wavelength goes up, the frequency must go down for C to be a constant. And looks like we're ready for our first practice problem. Ready to fire up your calculators? Yeah. Your tablet's not working. We'll do it on paper here. All right, so the first one says a certain photon of light has a wavelength of 710 nanometers. Uh-oh. Remember, wavelength needs to be in what unit? Meters. So we need it in meters, but it gave it to us in nanometers. Awesome. Calculate the frequency of this light. So our equation again is this. So what are we looking for? Which variable? V. So what do we do with lambda? Divide on both sides. Good. So we're going to move lambda down. So now our equation is C over lambda equals frequency. Okay. So be sure to show that. And I'll give you a heads up. C will always be on top. Okay. It has to be. Because if we're looking for wavelength, then frequency is going to be divided, and it'll go down here. Okay. But we're not looking for that. Go away. Okay. So here we have our speed of light, which is 3.0 times 10 to the 8, and I will give you that. I'll give you that. And that's meters, and I'm going to put second right there. Okay. Instead of doing double division lines, how I talked about earlier in the year. Now the wavelength, we got to do something with that. Since we have nanometers, we need to change that nanometers into meters. So what do we do with the unit nanometer? Move it diagonally. Which one's bigger? Or can we convert a nanometer directly to a meter? Yeah. Which one's bigger, meter or nanometer? And how many nanometers are in a meter? 9. Good. So 10 to the 9. So when I multiply 710 times 10 to the 9, that gives me 7.1 times 10 to the -7. Is that right? 7.1 times 10 to the -7. Okay. So we'll plug that in. So 7.1 times 10 to the -7. And that's meters. So, again, showing our units. Okay. What units can cancel out? Meter. Good. So meter goes away. What unit do we have? 1 over seconds. Remember, if you're looking for frequency, just like yesterday, it's 1 over seconds. Okay. So if you are wanting to write down seconds, or maybe it might be smart to go ahead and calculate the number and then write seconds underneath, that's going to keep you from doing something silly. So let's see here. Find out what that is. Like 4.23. Where did I get that? Times 10 to the 14. Now, let's keep this in mind. Whenever we look at frequency, it should have a high positive value, okay? Because there's going to be a lot of those wavelengths. If we have a negative on there, that means that we have less than 1 per second. and light moves pretty fast. So if you ever get like a negative number for a frequency, okay, question yourself. Say, wait a minute, I thought these things move fast in a second. And they do. They move at the speed of light. Okay. All right, everybody good on that one? Let's take a look at the next one. It says, calculate the wavelength for a quantum of light or a photon with a frequency of 3.45 times 10 to the 16 hertz. Okay. So again, we're still using our speed of light. But what are we looking for now? Frequency. So that means we're going to divide wavelength on both sides. Oh, no. You're right. We're looking for wavelength. Okay. So that means we're going to move frequency over. Thank you. So now we have, I thought we just did that. So there is our equation. Be sure to show that before you starting work there. And again, speed of light, 3.0 times 10 to the 8 meters per second. Do we need to do anything fancy to the frequency? I would make sure that I change the hertz to 1/seconds, because what we don't want to do is we don't want to put the unit hertz within the math, because that doesn't help us out. Now, so I'm going to put the number in here, and I'm going to show you what I'm going to do to the unit, just to help you out. Okay. So there's the number. If I write 1/seconds, okay, technically that's right. But also, if you do this, what does that equal to? Seconds. It's equal to seconds, right? Because you have 1 divided by 1, and then this, the seconds, since it's on the opposite side of the division line, it's going to go right there. Okay, so it makes sense to go ahead and not write 1/seconds like, 1/seconds like that, but put it up here. And I always do that. I put it in parentheses to show that it was on the opposite side originally. Yeah, Peter. The shortest what? Yeah, some wavelengths are huge. Are you talking about how small wavelength is? They can get really small, especially with the gammas. The wavelengths can get really, really, really small and have a very high frequency. But radio waves are like, some of them are 6 to 7 miles in length. But they still move at the speed of light. Okay, so what happens to the units here? Can anybody cancel out? Who? Seconds, yeah. So the meter stays in play, and we want it to be there because when we talk about wavelength, we're looking for a length there. So let's find out what that's equal to. And should we have a positive or negative exponent? So I'm 8 divided by 16, a positive 16. So that should give me a negative exponent, right? Since my number's bigger on the bottom and it's a positive number. So 8.70, we'll say, times 10 to the negative 9, and that's meters. Now, what's that? Okay, so make sure you type it in. So we'll go 3EE8 divided by, use your parentheses, and however you put it in. So like I do 3.45, but if you do times 10, you do times 10, caret 16, close that parentheses, and I'll bet you you'll get what I got. Okay. And think about it. You're doing 8 divided by 6, so that's a positive 6. I'm sorry, positive 16. So it's like 8 minus 16 when you do the division there. You guys get it that time? Yeah. We want to change the hertz into seconds because if I put hertz in here, how am I going to cancel it out? How could I? Okay, so what I did originally, I had it as 1/seconds. And I don't ever want to put hertz in the math. So I want to make sure that it's a unit that I can cancel out. Yeah. So hertz is this, is equal to 1/seconds. Okay. Which I think we talked about that yesterday. Yeah. How many zeros was it? And then an 8. You didn't count the thing over. So I changed the scientific notation. So, oh yeah, I see what you're saying.
But I didn't have that.
Scientific.
The white paper.
So it just rounded it up.
That I lost it. I used it on Saturday.
So second DRG arrow over. Yeah. The 1 is implying number of waves. Yeah, but we're not actually addressing that because nowhere in the calculations, and I think that's why they cheated and did that, because they wanted to say that represents a number of waves, but they didn't want to come out and say waves. And I think in computer jargon, when we talk about hertz, it's how many bytes go through the processors during a certain number of time. I don't know. Is that right? Is it bytes? Okay. So that it's an implied unit for that. All right. So everybody good on the math? Okay. All right. And then, so part of the homework is the 2's here. All right, so here's the bright line spectra. This is what I was talking about earlier on being able to identify a substance by looking at its bright line spectra. Unfortunately, I'm not aware here at Plainfield that we have the glass tubes. If we do, I'll set up a demo. I don't know where. There's no dark room because some of the sunlight that comes through will interfere with that. And I know that it might be difficult to be able to see the lines here. Like there's a red line there, a blue line there, and then some other lines here. This is actually the fingerprint of an element or a compound, so to speak, once you get into bigger things. And we can use that bright line spectra to actually identify what it is that we're looking at. And when we look at elements that have more orbitals and more electrons, this bright line spectra gets more and more complicated. Here with hydrogen, we only have 1 electron, and I'm surprised it actually emits 4 bright lines on that. But that's the fingerprint. So we could use that information to help us determine what element or compound that we actually have when we're looking at a substance. We can excite it, it emits a light, we can take a look at its bright line spectra and determine what it is that we're looking at. Unfortunately, we're not going to do a whole lot with the bright line spectra because you're never going to have to memorize them. There's literally millions of these different bright line spectra that they use and compare when looking at substances. So I just wanted to show that to you. So the other homework here is the 3's, and there's a couple on there. Okay, and a lot of these questions deal with what we talked about in the earlier section. Okay, so 2's and 3's, and then tomorrow I will give you a review, or you already have it, but the review worksheet for the quiz. Questions? It wasn't too bad.